going to look a little bit more closely at each of the oxidation and reduction halves of the reaction, aka half reactions. At the end of this week, I will upload a video explaining how to balance redox reactions, because that's a whole thing. So we're going to look at each half reaction first so that we fully understand exactly what each half reaction means. So oxidation is a reaction in which the atom or ions of an element increase in oxidation state. They increase in oxidation state because they are losing electrons. An example is the combustion of metallic sodium in an atmosphere of chlorine gas. What you're seeing in the video is a conical flask that is filled with chlorine gas, which is that yellowy hue that you see. And I think he's already dropped in a piece of sodium, but with like a lot of reactions, you can't just put sodium and chlorine together and then blah, they like make salt. You need that catalyst, you need that activation energy. So putting a piece of solid sodium inside a flask filled with chlorine gas is not just going to magically like poof and make salt. You need some kind of source of activation energy. So in this case, what he's going to do, if you remember from grade 10, I think we did this, you put sodium with water that has a tendency to produce a bit of energy through like sparks and fire and things. So what he's going to do is he's going to catalyze this reaction by dropping water on top of the sodium, causing it to react and then produce that energy needed to start the reaction. There it goes, dropping water, sparks. And there we go. Super bright. So what you're seeing floating in there now is very tiny salt, very tiny salt particles that are being suspended in the air. And rather than wait, I can fast forward because you have to wait for that all to settle. All right, now you start seeing, he's pointing at now the piece of salt, which you see is really nice, bright white color and little specks. Yeah, there we go. There's salt and you see a couple little specks here on the side of the glass, but that's really what you have left. That's a nice big chunk of salt left over. Okay, so let's break down what just happened. The sodium ions and chloride ions are made during an exothermic reaction. They form a cubic crystal lattice. The sodium cations are ionically bonded to the chloride anion. So we create positive sodium ions and negative chloride ions, and they form an ionic bond. So this is the overall reaction. The formation of the sodium ion shows of sodium because each sodium atom loses an electron to become a sodium ion. So we put the oxidation number directly above the symbol of the atom and the ion. So if we want to write a half reaction for the oxidation of sodium, we write it like this. We start with a sodium atom, which remember from rule number 1 for oxidation state, atoms that are in their pure state have an oxidation number of 0. And we form a sodium ion because we lose an electron. And the sodium ion is a monoatomic ion, so it has the same charge as it would as an ion. So that is oxidation. And notice the increase in oxidation state. We've gone from 0 to +1. We have increased oxidation state. Okay, so we say that the sodium has been oxidized. It's oxidized to a sodium ion. Reduction is where the oxidation state of an element decreases because something in a chemical reaction, whether it's an atom or an ion, gains electrons. So each chlorine atom accepted an electron and becomes a chloride ion. So we use this half reaction So one thing that I'm going to point out from the beginning is that when you balance redox reactions, it's going to be very tedious. It's going to seem like, oh my God, because you have to separate the half reactions and there's a whole thing, like I said before. But what I want to burn into your memory now is it is mainly for every part of it, it's a two-step process. The first step is to balance the atoms. The second step is to balance the charge. So if I start with Cl2, that's going to be behind my face, isn't it? So if I start with Cl2, because chlorine, remember, is a diatomic element, and we're going to form chloride ions, automatically I know that the chloride ions are not balanced with the chlorine, so I'm going to have to put a 2 there. And then you balance the charge, and because it's reduction, it means you gain electrons. That means electrons have to be on the left-hand side, and we gain 2 electrons because you have 2 negative charges on the right-hand side, and you need 2 negative charges on the left-hand side. So I just want to bring that up now so that it's a little bit less shocking later when I talk about it in a video. So this shows you a clear reduction because we've gone from 0 to -1, which is a decrease. So the species that undergoes a decrease in oxidation state is reduced. So the chlorine atom is reduced to the chloride ion. Now, these always have to happen together because electrons that are produced in oxidation are acquired, not required, are acquired in reduction. So in order for oxidation to happen, reduction must happen as well. And on top of that, the number of electrons lost must equal the number of electrons gained. And that's what makes balancing redox reactions a little bit messy because you have to account for that. In our last example, we had, let me go back, nope, here. Yeah. So in our oxidation reaction, we are only losing 1 electron. But in our reduction reaction, we are gaining 2. So this is obviously not the final overall equation because you would have to account for that. But I'm just letting you know, like, that's one of the things that you have to do. The transfer of electrons causes changes in the oxidation states of one or more elements. So together we call it an oxidation reduction reaction or redox. This is any chemical process in which elements undergo changes in oxidation number. For example, for another example, when copper is oxidized and nitrate form from, copper is oxidized and the nitrate in nitric acid is reduced. Sorry, I wrote that very terribly. I apologize. So you have copper and nitric acid. The nitrate's going to be reduced. The copper is going to be oxidized. So let's see how that looks like. By the way, this is, if you don't know, this is a penny. This is a form of US currency, and pennies are made using copper. So pretty vigorous reaction. Nitric acid is one of the worst acids, by the way. It's very, very damaging for proteins, which means, like, I don't know, your skin. Okay. So if you write oxidation or reduction alone, it's called a half reaction. So there's going to be a whole lot of things happening here. I don't want you to worry about the whole thing overall. You will eventually be like, yeah, but I know what that means. But what I want you to look at just for the moment is here, and don't worry about how it's balanced at all, and here. These are your half reactions, and they're already, this is like what you would see from balancing overall. It wouldn't start like this. So the overall equation is the sum of the 2 half reactions. At the end, the number of electrons has to be the same for oxidation and reduction. So if you lose the same number of electrons that are gained, they will not appear in the overall equation. So you can see from this balancing, you've got 6 electrons here and 6 electrons there. That's what has to happen. So they would cut. And I'm going to try to trick you. If there are no atoms or ions in a reaction that change oxidation state, it's not a redox reaction. So please make sure to check, because I will throw reactions at you that are not redox just to try to trip you up. Another big clue is if something is oxidized, something else must be reduced. So if you do find one thing, you have to have both. An example is, I'll write it out. Sulfur dioxide gas dissolves in water to form acidic solution of sulfurous acid. So sulfur dioxide dissolves in water. Do we remember how to translate word equations into chemical equations? If not, I might throw something at you to practice that, because I know you guys have, you guys have SAT coming up. The last one, is that done already? Is that this month? Oh my God. Maybe we'll do some of that too. Okay, sulfurous acid is H2SO3. So let's practice writing our oxidation numbers. Remember, they go straight on top. So I start here, oxygen's -2, times 2 is -4. This has to equal 0, so sulfur is +4. There's only one. That's a circle, not a 0. There's only one here, so that's +4. In the beginning, by the way, I want you to practice assigning oxidation numbers to everything. I'm guessing by probably early to mid next week, you will be able to suss out or to figure out which elements to target first. Typically, hydrogen and oxygen are the last. They almost are never really involved. It's usually things like sulfur, nitrogen, carbon, phosphorus, things like that. Okay, so -2 here, -2 +2. Now, because there's 2 hydrogens, I have to divide by 2. That makes each hydrogen +1. Now I go over here, do the same thing. -2 times 3 is -6. That has to equal 0. This is +1 times 2 is +2. So +2, +4. Now look at that. Nothing changed. Here, sulfur is +4. Here, sulfur is +4. Oxygen's -2, -2, -2, hydrogen +1, +1. Nothing changed. This is not a redox reaction. This is what I mean. Another example, when a solution of sodium chloride is added to a solution of silver nitrate, an ion exchange reaction occurs and white silver chloride precipitates. So, assigning oxidation numbers to everything, again, you see nothing has changed. And again, in this example, it's not an example of a redox reaction.